Section 8.2, Integration by Parts. Sometimes you will have a product of functions in the integrand which do not fall into any of our integration patterns. This usually happens when the integrand is a product of algebraic and transcendental functions, such as the integral of x times e to the x dx, or the integral of x times natural log of x dx, or the integral of e to the x times sine of x dx. Then we need a technique called integration by parts. Let's see where it comes from. If I am going to take the derivative of a product of functions, u times v, we know that the product rule says that it would be u times the derivative of v with respect to x plus v times the derivative of u with respect to x. Now we know du dx can be written as u prime and dv dx can be written as v prime. So our derivative with respect to x of the product of two functions is uv prime plus vu prime. Now, we know that uv is going to be the integral of the derivative of uv. Recall, we know a function defined as an integral looks like this. So it follows that the product uv is equal to the integral of uv prime plus vu prime dx. Now we know that u prime and v prime must be continuous because to integrate we have to have continuous functions. This becomes making into two separate integrals the integral of ub prime dx plus vu prime dx. And if we recall, v prime is dv dx. So the dx is canceled and I get the integral of u dv plus, likewise, u prime is du dx, dx is canceled, the integral of v du. And therefore, if uv is the integral of u dv plus the integral of v du, then let's just take one part of that. The integral of u dv would be uv minus the integral of v du. Now this is your integration by parts rule. The integral of u dv is uv minus the integral of v du. So clearly, to use this rule, we've got to be able to anti-differentiate dv, and we will need to anti-differentiate du. If u and v are functions of x and have continuous derivatives, because we need to anti-differentiate them, then the integral of u dv is uv minus the integral of v du. Let's look at an example. The integral of x times e to the x dx. You see, we can't use u substitution here because the derivative of e to the x is e to the x. If I just let my exponent x be u, the derivative of e to the u is e to the u times u prime, and if u is x, the derivative of that is just 1 dx. So the method that you know at this point does not work. So this integral will have the form integral of u dv if u is equal to x and dv equals e to the x dx. Therefore, if u is x, du is dx, and if dv is e to the x dx, we know how to anti-differentiate e to the x dx. Now, we're ready to go, and let's look at our formula. The integral of u dv is uv minus the integral of v du. You know what we're going to do? We're going to make a little chart. So we have decided to let u be x. So we need u and its derivatives. And whenever one of your factors in your product of your integral is polynomial, that is usually what we want to use as our u, because eventually it will have a derivative of 0. And then we need the other part of our product to be the dv that we can anti-differentiate. And we know that the antiderivative of e to the x just continues to be e to the x. So using our rule, here is our u times v minus the integral of v du. Oh, we know the integral of e to the x dx. It is e to the x plus our general constant c. Once again, what did we do? We took a product and we anti-differentiated a product. Now we're going to look at the integral of x times the natural log of x. We have to choose one of these to be our u and one of them to be our dv. Since we do not know how to anti-differentiate natural log of x, this needs to be our u. So our u is natural log of x, and its derivative would be 1 over x dx. And our antiderivative is dv equals x dx, and we know how to anti-differentiate that. And here we go. So we are going to make our substitution now. The integral of x ln x dx is u times v minus the integral of v du. Now let's see if we can clean that integral up a little bit. We can certainly bring this in front of the natural log. It just looks better, but let's look over here. The x into the x squared leaves x, and I can bring the 1/2 out. We know how to anti-differentiate this. That's easy. And there we go, and clean it up. Notice that I have x squared over 2 as a factor in both of these terms, so we factored it out. And here is our nice, pretty answer. Sometimes we have multiple integrations that are needed. Look at this problem, all right? Both transcendental functions. I'm going to let u be e to the x, and du is e to the x dx, and that would make cosine x dx my dv, and then anti-differentiating that gives me sine of x for my v, and we're going to do our substitution. So at the integral of e to the x cosine x dx is u times v, e to the x times sine x, minus the integral of v du. Okay, v du. Now, let's look at what happens. It says here we can keep integrating because this right here looks a lot like what we started out with, except for now, instead of cosine, I have sine. So I'm going to repeat the whole process again with my u being e to the x, but this time my dv is going to be sine of x dx. Now we know if our dv is sine of x dx, v, the antiderivative of that would be negative cosine of x. So here we go again. Here is my original problem. Here is this piece. And now we're going to anti-differentiate this. And let us notice it's following a negative sign. So we have to be careful with our parentheses. And here's my u times v minus the integral of v du with my new integral. And we're going to clean that up a little bit. And now let's look at what we have again. We're back to where we started. Oh, gee. So let's clean that up a tad. What we know is the integral of e to the x cosine x dx is e to the x times sine x plus e to the x times cosine x minus this integral that we started out with. Well, we already know what this is going to become, and we know if we keep doing this process, we're just going to keep going forever and ever. So there's got to be another way, and there is. What if, thinking about this as an equation, I brought this integral over here to this side of it? That would give me 2 of them. Oh, and now I could solve for this integral by dividing by 2. Now you will notice I carried a C1 all the way through because at the end I wanted to, when I divided by 2, to let C1 over 2 be my general unknown constant, C. Wow, that's tricky, huh? All right, let's look at cosine squared of x dx. Let's consider that as cosine x times cosine x. So one of our cosines is our u, there's our du. One of our cosine x's is our dv, and there's our v. All right, fine. So the integral of cosine squared x dx is u times v minus the integral of v du. Well, I can see that this is going to give me minus minus plus sine squared x, and I can go through the same process, or I could use a Pythagorean identity for sine squared. After my Pythagorean identity, I can make 2 separate integrals. I know what that's going to become, and we just did this. We know that this is going to keep going. So I can do the same thing here that I did with example 3, which is move this integral over to this side of the equation where I now will have 2 of them, anti-differentiate this, and then divide by 2. Now here is something really, really neat. If one of the functions in the product is one whose derivative will eventually be 0, and the other is a transcendental function which continually has an antiderivative like e to the x or cosine x, etc., the tabular method, or sometimes it's called tic-tac-toe method, is useful. So if I look at this one here, evaluate the integral of x cubed times sine x dx. First of all, we're going to make a chart and alternate our signs, plus, minus, and so forth. And then we're going to choose u, which is the one that is going to eventually have a derivative of 0, and start with u and list its derivatives until they get to 0. And then we're going to list our dv and antiderivatives until they all line up. And here's how this method works. I have, now remember, the integral of u dv is positive u times v, so positive u times v, minus the integral of v du. But all I have to do is plus this minus that product plus that product minus that product, and when I get to 0, I'm done. And then you add the signed products. It's very, very neat. Your TPs are numbers 1 through 4 all, that's matching, no working it out. Numbers 5, 7, and 9, which is identifying your u and your dv, no working it out. And numbers 11 and 13 where you work it out. See you next time.